Good night, everyone, and welcome back to Fundamentals of Engineering with Farhad. Mechanics of Materials supports reaction calculation. We have solved this example, this 1-degree indeterminate beam with the distributed load of W with the help of elastic curve, and this time we want to solve it with the second approach. So to calculate the reactions. So in this example, if you have a close look to the problem, it's 1-degree indeterminate, and then we have to solve it with either solution 1, which is determination of elastic curve from moment equation, which we have done it with in the previous video. I will provide you the link to this video if you want in the description of this video. And this time we want to solve it when we consider the moment at A as a redundant to convert our problem to determinate beam, then solve it. Then in solution 3, consider RB as a redundant, and finally we'll solve with the Castigliano's method. The current video is about to solution to consider the moment at A as a redundant. So if we consider the moment at A as a redundant, our problem dissects to two determinate beam, two simple supported beam, one of them handling distributed load of W, the other is just a simple supported beam with the moment M sub A. And by applying the superposition of those effects, we can get the reactions at RA and RB. So for the first part, which is two simple supported beam with a distributed load, with the help of moment area method, we'll draw the shear diagram and then the moment diagram. And then if you want to calculate the delta maximum, for example, for such beam, you can have it like tangential deviation of B with respect to A, TB with respect to A is area under M over EI times X bar, which X bar is the centroid calculated from B. Or because A and B's are the same, we can consider also like this one here. So our moment is a second degree curve with the equation of a parabolic spandrel like y is equal to k times x squared. This area is our moment. So this greenish area, that's TB over A, which is M over EI times X bar, which is calculated from B, but because it's located at center, both of them are equal to L over 2. So the area of this one of this greenish area is 2/3 of WL squared over 8 EI times the length, which is L over 2. We have two of them, then times the distance from centroid to the B, which is L over 2, and it just gives us TB tangential deviation of B with respect to A is equal to WL to the 4 over 24 EI. And for the second part, if you draw the moment diagram for this part, it just simply says this time tangential deviation of B with respect to A is A2 times the X bar, which is 2/3 of L from B. And if you do the math, just be careful, this area is a negative area, and it just gives us a negative M sub A L squared over 3 EI. And by applying the superposition, the tangential deviation of these two parts together is the tangential deviation of the total beam, which we know because B is like there is a pin there, there is no upward and downward motion. So we know that tangential deviation of B with respect to A is equal to 0. We already calculate these two parts separately, and if we add them together tangential deviation of b with respect to a due to loading plus tangential deviation of b with respect to a due to moment at a. If you add them up together, which we already calculate them, the only unknown of these equations are m sub a, and it just gives us m sub a is equal to wl squared over 8. As soon as we know what ma is, we can move back to our beam, and by, for example, beam one of those beam and summation of moment about a goes 0, it just gives us ma plus rb times l equal to 0, and it simply gives us the rb is equal to negative ma over l, and negative, it just says rb is downward. Ra should cancel out rb, so Ra is a positive ma over l, so Ra is wl over 8. These reactions are related to beam number 2. If you remember, we dissect our beam to two simple support beam, one with the effect of distributed load, the other with the effect of moment, and then we have to add them up together to get our original shape. So as soon as we have our moment, we can add the reactions for both of these beams, add them up together, Ra due to loading plus R sub A due to moment. And if you remember, you can easily know the reaction of each of these support for the distributed load is WL over 2. We already calculate the Ra for this part is WL over 8, and if you add them up together, it just gives us Ra is equal to 5 over 8 WL, and Rb is equal, definitely is equal to the leftover of W, that's third over 8 WL. Thank you. We'll solve this problem with considering Rb as a redundant in next video. Thank you.